Talk about going, they have testing facilities out
Uh-huh. Okay, we start something fun today. Today we start Unit 2. We start our talk of really the first big topic in calculus. This has all been prep work. Now we're getting into differential calculus. This is really, hasn't even really been calculus yet, but now we get to start calculus. We're going to start with some non-calculus stuff though. Average rate of change. You guys know what this is. Like, who's in physics? Okay, some people. Okay. Not many, but some. But even if you're not, you're going to learn some physics in here starting now. Today we kind of get into some physics. Oh, I mean, really not today a ton. So you guys know one average rate of change you've talked about in physics would be like average velocity or average speed. And what is that? Yeah, what would be like average? I mean, velocity and speed are not interchangeable, but we'll just say they are. For now, we can treat them as being interchangeable. Like if you were to, you're right. You're right. So, but we'll ignore the vector nature for just a little bit here. So if I wanted to calculate an average velocity, we'll say velocity because that's better, because that is a vector quantity. Average velocity, what is that equation? It's super easy. Even if you're not in physics, you know it. Delta what? Oh, you guys call it D. Okay, yeah. Yeah. Okay. Usually you'd say delta S. S is displacement. You don't want to choose D because of what we're doing starting now, because derivatives use D's, and so that's a little confusing. So usually we'd use S's in physics. So average velocity would be displacement, meaning change in position or change in distance over change in time. And you all knew that. Like if we go to Hermiston and we say we take a trip to Hermiston and it takes us, let's just say hypothetically it's 30 miles away where we're going, and it takes us half an hour to get there. What's our average speed or our average velocity?
A mile per minute.
Okay, in more traditional units?
60 miles an hour.
60 miles an hour, right? Okay, are you guaranteed to have gone 60 miles per hour the whole way? No, but it doesn't matter. The average doesn't care. The average rate of change there, the average velocity in this case, which is the average rate of change of position, is 60 miles per hour, regardless of what the specifics were. All it cares about is starting value and ending value, right? Okay, so in math, an average rate of change always corresponds to the slope of a secant line. What's a secant line?
A line that locally intersects the curve in two places.
Very good. Okay, so this is different than a secant function. A secant line just means a line that specifically intersects a curve in two places. Okay, so for example, the red line is a secant line relating to the blue curve because it intersects the blue curve in two distinct places, right? The slope of the red line represents the average rate of change of that blue function over some interval. We can call it delta x. When x changes by that much, what does delta mean in math? Change in, yeah, right. So when we say delta in math, it means change in something, whatever follows the delta. So this is change in x. When x changes by that amount, the average rate of change of our function is given by the slope of that line. Is the rate of change always that? No, it changes, right? It's a curve. So we can see that, like if I wanted to describe what's going on here, it looks like at the bottom, the blue function is not changing very quickly, right? Its y value is staying pretty much the same, but as we move along the function, its slope gets steeper, and so it starts to change its output value, its y value, more aggressively towards the end of that interval. But on average, the slope of that red line represents, on average, how quickly the slope of the blue function is changing as x changes. Okay, give me 1 to 5 on that. Is that you getting kind of a conceptual idea of what's going on there? Okay, so an average rate of change is just the slope of that secant line. Well, what's the slope of a line? It's just rise over run, right? Aren't you used to seeing delta y over delta x, change in y over change in x? Okay, well, what's change in y? If the blue function is f of x, then aren't the coordinates of this point right here, if this is at an x value of x, let's say, right? The coordinates are x, f of x. The input is x and the output is whatever the function gives us at x, f of x. If we scoot over to the right some amount delta x, then what did our x coordinates become? Well, they changed from x to x plus delta x, and so the output would just be f of that, f of x plus delta x, right? And so what's the rise then? Well, delta y is just going to be that y value minus that y value. The red y value minus the green y value, okay? So delta y is f of x plus delta x minus f of x. What's the run? Delta x, right? Delta x means the change in x, right? So that's already taken care of. So this is really important. We're going to come back to this many, many, many times. That represents an average rate of change, the slope of the secant line. Okay? So usually we like to deal, physics is a great model for calculus. And kinematics, right, the study of motion, is really a good one, right? So instead of using x's here, we're going to use, well, we're going to use t's. So I got to change this. So this should have been the t-axis. Because in physics, usually our input variable is t, right? What are we interested in doing in physics? Well, we're interested in looking at how some system evolves in time, right? Like if we're looking at kinematics, maybe we're shooting a cannonball out of a tube and we want to see what's happening to that cannonball as time passes, right? Kinematics is going to describe the motion of that cannonball as time progresses, right? So usually time is going to be the input or the independent variable, and we're measuring some output quantity of interest relative to that, like position, s. Okay. So we start off with the ordered pair. Input is t, output is s of t. Some time delta t later, t is changed. The output or the input is going to be t plus delta t. The output is s of t plus delta t. And so our secant equation, the slope of the secant line, it just is going to evolve. Instead of having x's and y's, it's going to look like, for us now, this becomes slope of the secant line is going to be delta s over delta t, right? So it's going to be s of t plus delta t minus s of t over delta t. And that is the equation of what quantity in physics? What is that? What's the rate of change of position with respect to time? Average velocity, right? That's average velocity. Okay, so if we think about this now, this picture makes a little more sense, right? If we look at this picture, it has some meaning. It's not just abstract. Position is something, right? Now let's make our movements really simple here. The position is gonna refer to position along a straight line at the front of the room. Okay, so it's really simple. And we're gonna say right in the middle of the board is 0. That's s equals 0. We're gonna arbitrarily call that point 0. So this would be a position of positive 1 meter. This would be a position of negative 1 meter, right? Because position is a vector quantity. That's the positive direction, we're gonna say, and that's the negative direction, okay? And they're different things. It's not like distance is always positive. Distance is what we call a scalar quantity, right? Always positive. What distance is useful to us, like if we talk about taking a trip to Hermiston, we say, okay, we just traveled 30 miles. If we travel to La Grande, well, how far did we go? 40 miles. We don't say something like Hermiston is positive 30 and La Grande is negative 40. That doesn't make any sense, right? To us, we just want to know how far am I going to have to drive in my car to get there, which is a measure of distance, which is always positive. But driving 30 miles in one direction on the freeway is different than driving 30 miles in another direction. The outcomes are very different. We end up in different places. And so if we want to really be specific, we do need to use a vector quantity like position instead of distance, right, or displacement. Then there is a sign associated with it. The sign is kind of cumbersome when you're dealing with directions, like map directions, because negative and positive don't make sense. So what do we do instead? Like north versus south, east versus west, right? But they mean the same thing, don't they, right? Mathematically, it's easier to think about this in terms of a positive and a negative, right? And we could just define, like, say something like east is just negative west, and it would work, okay? So what's this saying then? If we're traveling along a line here, can somebody describe that interesting story that's evolving from here to here? What's happening? It's accelerating, right? Does that make sense? How do we know that? Well, look at that blue curve. It looks like the position is changing with time, but it's changing pretty slowly because that position right there is really not very different from the starting position, right? Didn't change much. But up here, between that point and that point, well, it changed by quite a bit, right? So where would the object that we're describing here be going faster? Over here, right? Agreed? Okay. Down here it's going a little slower. On average, how fast is it going over that interval? What's telling us? The red line, right? The slope of the red line is telling us on average how fast did it go. Okay? Everybody see that? And to get from this point in space-time to this point in space-time, right? What's space-time? It sounds really, really complicated. It's not. Space-time just involves a position and a time, right? So there's some position. Our space is simple. It's just a line. This position in space-time is that point at that time, whatever that time is. This point in space-time is really, it's just that new position, which is further to the right at a later time, okay? To get from that first point to that second point in space-time, we could either travel this accelerating path where it starts slow and picks up speed and eventually is going pretty fast, or we could put on cruise control and just go the same speed the whole time. Either way, after a time delta t has passed, we're going to end up at the same position. Agreed? Okay, everybody get that? And so in a sense, when we talk about an average rate of change, really what we're doing is we're saying, okay, let's take the easy case of cruise control. If we were just to travel at the same average speed the whole time, what would that speed be? Okay, give me 1 to 5 on that. Is that making sense, kind of what we're saying here? Okay. So let's remind ourselves about kinematics quantities. And some of you aren't in physics, so this is going to be a little bit new. If you're not in physics, take it in college, because it's like the best thing you could ever learn. Physics is so cool. It explains everything. It's just awesome. So the input for kinematics is t. That's going to be our input or our independent variable. What are the different output functions we could talk about? Well, position, s of t. When I have that little kind of a arrow over a quantity, that means it's a vector, which means it can be positive or negative. There's a direction associated with it. So we could call that x of t or y of t, or it could be some combination. Like we could be traveling in 2 dimensions, just in any direction we want to, or in 3 dimensions. We'd have to add, there's an x component and a y component and a z component, but we'll get to all that stuff later. We have average velocity, which is going to be our rate of change of position, or delta x over delta t, or delta s over delta t, whatever we want to call it. We have average acceleration. For those who are in physics, how is acceleration related to velocity? Change in velocity over change in time. Okay, so velocity is change in position over change in time. Acceleration is change in velocity over change in time. So acceleration is to velocity as velocity is to position, right? Okay, and if we want to get extra complicated, we could say that acceleration is the rate of change of the rate of change of position. Okay? Okay, so here's where you guys we kind of leave algebra-based physics, which is really all you're doing this year. You're really just doing kind of, you know, it's not as interesting because it's algebra-based. We're going to make it much more interesting by making it calculus-based, which gives us so much more power in physics. When you really want to start talking about instantaneous velocities, okay, you can't really do that effectively with algebra. That's where we're going to need calculus. Under certain very tightly prescribed circumstances, you can deal with this in a high school algebra-based physics class. If the acceleration is constant, for example, then you can kind of deal with instantaneous velocities and instantaneous accelerations and things like that. But once the acceleration starts to be non-constant, starts to be variable, you can't do it anymore. So you need calculus, which is where we're going with all this stuff. Okay, scalar quantities, the red quantities up here are scalar quantities. They only have a number, that's it. A number describes the entire quantity. The blue quantities are vector quantities, which need two quantities. They need a number, which is a magnitude, and a direction, right? Think speedometer versus velocitometer, right? The speedometer has one quantity. A velocitometer would be more complicated. It would give you a positive answer driving west down the freeway and a negative answer driving east down the freeway, for example. Okay? Okay, so let's just try some actual physics problems. Let's find the average velocity of this particle described by this motion here. That's supposed to be s of t. I don't know why it's all jumbled up there, but let's fix that. It's giving us a position function. So what does that mean? What's the position of the particle at t equals 0? How'd you get that? Plugged in 0 for t, and it gives you an output of position is 1. Maybe the units are meters. So on our front of the board, that would mean it's right here to start with at t equals 0, right? Everybody get that? So it's just a regular function. I inputted t, and that function output spits out the position of the particle at that time, right? So if we want to find the average velocity of the particle between these two times, t equals 2 and t equals 5, how would I do that? Think about that for a second. What's average velocity again? Okay, displacement. And displacement's a fancy word for just change in position, right? So change in position over change in time. How would I say that mathematically? What's the change in time for this problem? 3 seconds. How'd you get that? 5 minus 2. Okay. Okay, so now how would I find the change in position? Okay. So s of 5 minus s of 2. Okay, could I do it as s of 2 minus s of 5? No, it wouldn't make sense, right? It's got to be the final value minus the initial value. What does initial and final mean? Well, initial is starting value. In this case, 2 comes before 5. So t of 2 is the initial value of position. T of 5 would be the final position, right? So we get something like that, right? S of 5 minus S of 2, or 5 minus 2. Okay, give me thumbs. How are we doing? Does that make sense? Okay. So that's going to be the slope of our secant line, which is average rate of change. Well, S of 5, that's easy to find. We just plug in 5. And if we do that, what's that give me? Well, I'm going to get 25 halves minus 4. So minus 8 halves, so like 17 halves. minus whatever I get when I plug in 2 into my function. And if I just do that arithmetic, 17 halves minus 1 all over 3, it just gives me 5 halves if I just simplify that. Okay? So assuming my units are standard, meters and seconds, my average velocity would have been about 2.5 meters per second the whole time. Right, assuming we're using meters and seconds. I mean, it could be something else, but we'll use just standard MKS units. And if we want to look at this on Desmos, which is always fun to do, there it is, right? So there's the red function is my position function, right? There's the point at t equals 2, our position is 1. At t equals 5, our position turns out to be 8.5. And the green secant line is predicting the average rate of change. And what is that if we calculate that? 5 halves, right there. Okay? Make sense? Okay. All right. So for your notes, I've just got a picture of that. Okay, well, how could I find the instantaneous velocity of that particle at t equals 2? Yeah, I mean, if we go back, let's go back to that picture again. If we look at t equals 2, how could I describe how fast the particle is moving at that point if the red function is the position function? So what was the suggestion? Yeah, okay, so what's a tangent line? That's different than a secant line. A secant line, we said, was a line that connects 2 specific points on a function. And it might intersect the function in some other places incidentally, but we're looking at two in particular that we're interested in. That's different from a tangent line. What's a tangent line? Or a tangent to a curve. What is that? Okay, so yeah, so let's try. You guys help me draw a picture because I forgot what a tangent line is. So you're gonna have to help me out here. So I've got some function f of x, let's say, in general, and I want to find the slope of the tangent line at some particular value right there. We're going to call that value c. What kind of line is going to represent that? What are the characteristics of that line? How many times does it intersect the curve? Only once. Okay, so it could be, I got you, so it could be like that right there. Okay, that's not going to work. Okay, it's got to be, you were talking about something more specific. You meant something like that, right? Okay, so if I were to zoom in on that point really, really far and the curvature starts to disappear, because that's what happens when you zoom in on a curve, right? You can see why people once thought that the earth was flat, because it looks pretty flat. You go stand in the middle of a wheat field outside of Pendleton, it looks pretty flat, right? You cannot see the curvature. Very few people, really nobody would have had an opportunity to ever really see the curvature of the earth until recently. I mean, you can see it, like if you go up really high in a plane, you can kind of start to see the curvature, and if you go up really high in a plane that's higher than a commercial plane, you definitely can see it. And obviously you can see it from the moon, because astronauts could block out the earth with their thumb, right? So it's there, it was pretty obviously highly curved, from their perspective. But as you zoom in, you get closer to the surface, it looks pretty flat, doesn't it? So if we were to zoom in on this and that blue curvature were to go away, and we've seen this before, right? We looked at some examples like this, then the line and the curve would become indistinguishable. That's what a tangent line is. When I zoom in, the tangent line takes the appearance of the curve. As the curvature disappears, they look the same, and the function looks more linear. It starts to approach the tangent line. Okay, so that's what we mean by a tangent line. And doesn't it make sense that that's really what we're looking for? The slope of that tangent line right there is telling us, the steepness of that tangent line is telling us at that particular instant how fast is the object going, right? Does that make sense? Okay, so how could I somehow find that? I guess that's going to be our next question. We've got so that's what we're looking for, is that tangent line, right? And let's look at another Desmos file here. Okay, this one's a little different now. This time when I turn on the tangent line, there it is. Now watch what happens as I drag this point. The tangent line is changing its slope fluidly with the curve, isn't it? Right? Everybody see that? Okay. So that's the holy grail of differential calculus, is we've got to figure out a way to calculate instantaneous quantities like instantaneous velocity. How could I calculate that? Say it again. Very good question. In fact, that is the goal of differential calculus. Differential calculus was invented to answer that question. That very question is, how could we come up with that? Well, any suggestions? Let's say that we wanted to know how fast precisely we're going when we pass by a Rue elevator on the way to that big grain elevator on the side of the road when you're going to Hermiston. Okay. Well, okay, so we already said that, like, if it takes us a half an hour to get there and it's 30 miles away, then our average velocity was 60 miles an hour. Okay. Is that going to help us a lot when we're figuring out how fast we're going? I mean, a little bit. But does that mean we're going 60 when we go by the elevator? No, it doesn't, does it? How could we get maybe a better estimate of how fast we're going right as we pass by that one specific place?
Like just that mile.
Okay, just that mile. Okay, so let's say when we go by just that mile, it takes us exactly 60 seconds to go by the mile posts that include that elevator. So that would be a mile per minute, that's 60 miles an hour. Okay, that's a better estimate. Is it perfect? No, how can we do better? Oh, I could get it shorter. I could make it, what if I made it 100 meters? That's gonna be pretty good. My car's not gonna change that much over 100 meters. Maybe I do it over like 1 meter, right? Or over, the width of an atom or something. And eventually I get a pretty good estimate. So what does it sound like I'm doing here? This sounds a lot like stuff we've done in the past. Oh, okay, we're taking a limit, aren't we? We're taking a limit, and we're taking a limit of, I guess that was it for today. But let's not have that be it for today. Let's go back for a second. Let's go back to this right here. The slope of a secant line, right, was this stuff right here. Here's the slope of a secant line. This is average velocity, right? We could take a limit of that as what? As t? As delta t, which is the time interval over which we're making these calculations, approaches, okay, but as delta t, the change in t, if we want to get an exact value 0. Yeah, that's it. Okay, that's it, right? That's the big trick of differential calculus. If I want to come up with the slope of a tangent line, all I have to do is take the slope of a secant line and take the limit of that as the change in the input variable, delta x or delta t in this case, approaches 0. As delta t approaches 0, what's going to happen? Well, these 2 points are going to be drawn together and they're going to merge into effectively a single point, and so the secant line becomes what kind of line? The secant line becomes a tangent line, right? Because the 2 points that define the secant line, eventually as their separation goes to 0, they start to look like a single point, and you guys told me that was a tangent line. The line that intersects the curve at only 1 point and is parallel to the curve is the tangent line, right? So that's what Newton and Leibniz came up with differential calculus. They came up with this idea that by taking this limit, you can calculate this elusive quantity that's the slope of a tangent line that nobody had been able to figure out prior to that for hundreds and hundreds and hundreds of years. Okay? So that's where we'll kind of, like, that's the big find for the day. Slope of the tangent line is the limit of the slope of the secant line as, and we'll use x's instead of t's here, as delta x approaches 0. So it's the limit of f of x plus delta x minus f of x over delta x as delta x goes to 0. If I try to evaluate that expression directly, what do I get? 0 over 0. Is that a shocker? Didn't you know it was going to be that way? It's indeterminate, right? Which means we have to do some more work. We have to do some algebra to figure this out, okay? And this is, by the way, the definition of the derivative. That's what a derivative represents. When we talk about a derivative function, it represents the slope of a tangent to a curve. That's it, okay? So I'll just introduce the terminology or the nomenclature for a derivative, and that's probably good for today, I bet. Okay, here are different ways of saying derivative. If we know that the original function is y equals f of x, we could say the derivative as f prime of x. That's one way of saying it. That prime means change, right? So something is changed. We've taken the original function and we have derived a new function called the derivative, which is f prime of x. We can write this as, a lot of times we'll shorten that to just f prime, for example. We can call this dy dx, which is a really strange, like that ratio form is kind of a weird way of saying it, but think where that comes from. That evolves from, it makes sense in a way, because what's that? That's the slope of a secant line, right? Rise over run between 2 points. Well, if we're shrinking that delta x down to be vanishingly small, then that just evolves to be dy over dx, where the little d just means really small, right? So we're taking really, really tiny slopes of secant lines, and so that's a common notation. Sometimes we'll just call that y prime, okay? These all mean the same thing. And why do we have so many different ways? Well, it kind of contextually, first of all, each textbook author is going to like one way better than another, but it's kind of contextual too. If we're talking about specifically y and x and a graph of a function, sometimes dy dx makes sense to think about. But what if I want to say something like, what is the derivative of f of x equals x squared? I could write that as f prime of x, or I could do a hybrid, and I could say this: the derivative with respect to x of x squared. They all mean the same thing. They all mean the same thing. Those are just like a whole bunch of different ways of saying exactly the same thing. What's the derivative of a function? And it seems confusing now, but pretty soon you go, you just immediately recognize these are just different ways of saying the same darn thing. Derivative. Okay, that's it. And what does it represent? The slope of tangent line. That's it. The slope of a tangent line to a curve. Well, because y is equal to x squared. So that really is dy dx, isn't it? Because y is defined as x squared. Okay? But it's like saying, in this case, we're thinking about the derivative as kind of an operator. It's the derivative with respect to x if you fill in the blank. It's like I'm doing an operation of differentiating whatever I put in there. And that's the verb we associate with taking a derivative. To differentiate means to take, it's the verb of taking a derivative. Finding a derivative is to differentiate. Derivative is a noun. That's the thing that we end up with, is the derivative function. Okay? A lot of times people want to use the word derive. Derive is not the verb. The verb is differentiate. Yep. Say it again.
Differentiate or differentiate?
Differentiate. FF. D-I-F-F. Differentiate. Okay? So now you got the background. Tomorrow we'll dive into this a little bit.